Hi, I'm Jake, Department of Biomedical Engineering.
Hello, my name is Anand. I am a senior in aerospace engineering.
Hello, my name is Jack Picard. I'm a senior in applied physics with an emphasis in mechanical engineering and a minor in material science engineering.
I'm Darshan Sonawala, Department of Mechanical and Aerospace Engineering, and this is our presentation on the mechanical properties and behavior of basalt carbon hybrid FRP cables and their potential uses in bridge cables.
So this presentation will mostly cover how hybrid compositions improve various properties of an otherwise non-hybrid material. With the combined attributes of two material classes, the resulting alloy could have the best of both worlds. Our topic discusses how this combination could optimize the performance of bridge cables. The composite of basalt and carbon reinforced plastic has higher yield strength and better ductility than the most commonly used steel. Unlike steel with its low fatigue limit, FRP retains 55% of its initial fatigue load after 2 million cycles. An example where bridge length of this caliber becomes relevant is when we start talking about the longest bridge in the world, the Russky Bridge in Vostok, Russia, at a whopping 11,004 meters. Now, this isn't a problem for the average sized bridge, but once that length reaches over 800 meters, non-hybrid steel's equivalent modulus of elasticity starts dropping drastically, falling to only 75% of its initial modulus after 2176 meters, as you can see in the Ernst equation. BCFRP are impervious to this because of their low weight density gamma. Because steel is so much more dense, it does not stand the test at long distances, so we hope to strengthen future bridges by strengthening the cable component with specifically BCFRP. Although 100% carbon reinforced plastic does have higher fracture toughness, it's too expensive to implement, so BCFRP is more affordable at only a limited composition of carbon, but only trivially less effective.
So getting into the atomic description now, the first thing we're going to talk about is the composition of the basalt carbon FRP cables. The basalt FRP cables show a very low tensile strength as well as a high ductility, meaning that they can plastically deform over larger strains. On the other hand, the carbon FRP cables show a very high tensile strength, and according to the stress strain curve, where we see a fracture after ultimate tensile strength, these cables are brittle. When we combine the BFRP and CFRP cables with different ratios of basalt to carbon, we can see that both properties of both materials are shown in the hybrids. The range of ultimate tensile strength in these hybrids is close to the strength of CFRP, while in most of these hybrids we can see that rather than brittle fracture, there is some plastic deformation before fracture. One combination that we thought would work for bridge cables includes the 28% of carbon. This uh, combination is good because it leads to high ductility and a high tensile strength, as well as no sag effect when load is being applied on the cable. So moving on from composition, another thing to think about is stacking sequences. So there are many stacking sequences that can be created with carbon and basalt fibers. Um, these stacking sequences had a great effect when the samples underwent flexural loading, which led to both tensile and compressive stresses. Uh, one conclusion that we found from these stacking sequences was that when carbon fibers were placed at the surface that was going through compressive stress, the strength of that material increased. This is due to the carbon fibers absorbing much of the load on that end because of carbon's higher tensile strength. When basalt fibers were placed on the tensile and compressive ends, we saw that the material had a high ductility and also low tensile strength due to the properties of basalt fiber. So from these observations, we can see that uh, the stacking sequences play a major role, especially depending on the type of material on the outer surfaces of that stacking sequence. So an example of how composition and stacking sequences affect hybrid cables can be seen in the behavior of fracture of these different hybrids. So in some hybrid cables, we see that cracks that propagate through carbon fiber don't necessarily go through the basalt fibers. This is because of the ductility of the basalt fibers compared to the brittleness of carbon, where crack propagation is easier. These fractures that stop that basalt also help to strengthen the material, and it made sure that the material was still ductile as there was load applied on it and being deformed.
While there have been several different experiments done with BCFRP cables, there have been no bridges built yet available to the public. The first cable-stayed bridge to use FRP cables was the Leader Bridge, now called Aberfilly Bridge in Scotland, built in 1992 at a length of only 110 meters. Since then, more bridges of this style, designed for pedestrians and small vehicles, not commercial use, have been built. However, the expense of producing CFRP cables, let alone BCFRP cables or BFRP cables, has hindered the process of implementing BCFRP cables to public use. The price of carbon fiber over the last 20 years has been reduced to 1/5 of the originally at almost $40 per pound. With this material cost drop, we have seen more implementation of carbon fiber into things that were not feasible before, and it will soon carry over into the design of bridges more heavily. Companies that sell machinery for mining materials and ore out of the ground use BFRP cables because of their insulative properties. They can retain their tensile strength in temperatures ranging from -200 to +600 degrees Celsius. There is also a vibrational stability that the integration of basalt adds to the mix that is still being experimented with, as well as the different stacking sequences. Because BCFRP cables have been much higher resonant frequency due to their tensile strength and low density, it eliminates the possibility of cable vibration having resonance with the support pillars or the road surface. This is a big step up, as the vibrational frequency or the resonant vibrational frequency of steel is much lower and closer to the resonant frequency of the support pillars and the bridge itself, posing a likely threat with steel cables, but eliminates it with BCFRP cables. A study into the distribution of ring stress in the cables reveals that the outer layer carries most of this stress, while the inner layer is at the minimum stress level. This gives importance to the properties of what is chosen as the outer layer material. The two properties of insulation and vibrational stability is that basalt on the outer layer does give the reason to have basalt as the outer layer of the cable, but it is a trade-off because it has significantly less tensile strength but more ductility than the more brittle but higher tensile strength carbon fiber layer would have. This trade-off is part of the reason why BCFRP cables have not been further implemented into the industry, along with the cost in the past. Now, the sky's the limit with the possibilities and applications of BCFRP cables.
As for the future of carbon-basalt hybrids in bridges, we see several ways to optimize the process and to implement them in economically and ecologically friendly ways. In order to optimize the material, we first counter some of the issues that it has. One of these issues is delamination, or the process by which certain composite materials fail due to the materials separating into the layers that create the material itself, thus allowing the stresses to easily fracture the material itself. One of the ways we can circumvent this issue is to create adhesive layers. The addition of adhesive materials could help prevent the delamination by preventing the formation of these layers in the first place. Another possibility we need to consider is vibrational stress. As we know from previous catastrophes like the Tacoma Bridge disaster and so many others, vibrations and oscillations can be very dangerous for bridges itself. To prevent vortex vibrations from forming, we place the BFRP and CFRP material cables in separate concentric layers on the cable, which will reduce clashes between these two materials within the main cable itself. These two materials have been known to cause some vibrational stress when clashing during the testing phase. So to prevent vibrations, we turn to one of our research papers which talks about the benefits of viscoelastic materials in this application. To accomplish this goal, we would have both cable layers have a coat of viscoelastic materials surrounding it, basically keeping it from clashing, and due to the vibrational dampening effect of viscoelastic materials, this is a very sleek design and a very elegant way to counter this issue. Our hypothesis on the use of these cables is an optimistic one. The hybrid material could greatly benefit the structural integrity of bridge cables due to its tensile strengths and other material properties. It would also allow for a slow elastic deformation rather than a brittle one, which in the event of failure would be an instantaneous disaster. With proper oversight and regulations, the addition of this hybrid material could allow the officials enough time to make the repairs that are needed and ensure the safety of anyone near this bridge. This bridge is also very environmentally friendly. The material is very abundant in the earth and it's very easy to create. Uh, this material is also very economically friendly. So the addition of these changes and the addition of this hybrid into the cable itself would greatly benefit the properties that the bridge requires, and it makes it a very strong candidate for this application.